In this problem, we're given a graph of a function y equals f of x equals the square root of x, which is graphed in the color black, shown here. Along with the graph of the parent function, we have four other graphs that would match these four equations, which are transformations on the parent function. Here are some transformation rules that are in play in this problem. So for example, to pick the first one, if you take the equation of some function f of x, our function f of x is the square root of x, and this says if you multiply the output of the function, or the entire equation, by -1, that would look like this, and would match this equation here, that would reflect the graph of the parent function about the x-axis. Here's our parent function, the black curve. Reflection about the x-axis means if this was drawn with ink or paint and a piece of paper, and you were to fold the piece of paper about this dotted line, which is the x-axis, that ink would smudge down here and would become what we've colored in red. So based on these choices, the red graph matches the equation y equals negative square root of x. Another way to explain a reflection about the x-axis is if you had picked a point on the black curve, I'll make up a point, say 4, 2, and you left the x-coordinate alone, but you changed the sign on the y-coordinate. Remember that this is the notation for the output of the function. So when x is 4, the output comes out to be 2, but what we're doing now is we're changing the sign on the output. So if f of 4 is 2, putting the sign on the outside would mean that the output would no longer be 2, but would be -2. So this point 4, 2 would get mapped on the transformed graph to 4, -2. So think of a reflection about the x-axis as leaving the x-coordinate alone. I picked 4, and we stuck with 4. And whatever the y-coordinate comes out to be, we're in the business of changing its sign. So we changed the 2 to a -2. That would work for any point. Keep the x value alone, change the sign on the y value, and that would get you from a point on the parent function to the transformed function. Well, I could give a similar story for a reflection about the y-axis. The y-axis is very similar, except this time we're changing the sign on the x-coordinate, not the y. In terms of an equation, it would look like this. Here's my parent function f of x, and we're changing the sign on the input variable. Since the input variable is already underneath the radical symbol, when we change its sign, the negative will appear inside the radical as opposed to outside, much like the negative appears on the inside of the parentheses here, as opposed to the outside. So let's pick that same point, since we're familiar with it. Let's suppose this is the point, 4, 2, and I don't have any labels on this graph, so I'm making it up. Suppose this time we took the point 4, 2, and this time we are to change the sign on the x-coordinate, not the y. So changing the sign on the 4, that would be -4, leaving the output alone, which is 2, means the point 4, 2 would be mapped on my transformed graph to -4, 2. So the black curve would get transformed into the orange curve, or you can think of it as a reflection about the y-axis can be explained if this time we fold the piece of paper about the y-axis. If this was ink on a paper, and let's say wet ink, the ink on this black curve would smudge over here, and it would still be black, of course, but we colored in orange to differentiate the different curves. So all that was to explain and determine that this is the equation for the orange curve. Let's move on to the vertical stretch. A vertical stretch says that we're altering the output of the function f of x by multiplying by a number on the outside, and whether that number is bigger than 1 or it's between 0 and 1 determines whether it would be a stretch or a shrink, and sometimes we call them compressions rather than shrinks. So the equation that has a number being multiplied by my parent function that's bigger than 1 would be a 2 here. To get this equation, you could think of it as we're taking the parent function f of x, multiplying it by 2, so it's a new equation would no longer just be the square root of x, we're multiplying on the outside by 2. So what this does is leaves the x-coordinate alone, but takes the output, or the y value of any of my points, and multiplies by 2. So you can think of it as any point I pick on my parent function, I can find the point it would be transformed to by leaving the x-coordinate alone. We didn't change that. Notice that the input variable is still x, but we're taking the y-coordinate, the output, and multiplying by 2. Well, sticking with my example, that if you plugged 4 into the square root function, then the y-coordinate would be 2. So what this transformation does is leave the x-coordinate alone, and multiplies the output by 2 in my case because a is 2. So taking the y coordinate of 2, multiplying it by 2, so my y was 2, I'm doing 2y, 2 times 2 is 4, that's going to make the point 4, 2 get transformed into 4, 4. Notice that the blue graph has y values that seem to be twice as high above the x-axis than the y values in the black graph, and that's because we're vertically stretching it by a factor of 2. You need not even pick numbers. If you picked any x value, not even knowing what it is, we could compare the height of the y value on the parent function to the height of the y value on the transformed function. Notice that the height of the blue graph above the x-axis for this x value looks like this and is about twice as far above the x-axis as this point is on the parent function. So the blue graph matches this equation here. So lastly, we have this equation, which matches this transformation rule that says we're taking our parent function f of x, which in our case is the square root of x, and we're multiplying it by a constant that's between 0 and 1. In my case, it's a half, or 0.5. So now we're going to get a vertical shrink. In fact, we're taking the y values at any point on our parent function and we're cutting them in half. So the graph is going to be half as tall, so you may gather that the green graph is already going to be what matches this equation because it looks exactly like the black graph except the y coordinates are half as tall. If you like my example where I start with the point 4, 2 on the parent function, what that means to me is that when x is 4, we have a point on the parent function whose height above the x-axis would be 2 units. With this transformation, we're not changing the input variable. Notice it's still x. In fact, the only transformation in this list that changes the input variable is this one, where we changed its sign. So I'm going to leave the x value of 4 alone. However, this time I'm in the business of taking my y coordinate, my output, f of x, and multiplying by a half. So if this is y, my new y value is going to be a half of y. Half of 2 is 1. So my new point turns out to be on the green graph, and its y value is only 1, half as tall. And it's pretty clear that this height is only about half of the height of that corresponding point on the parent function. You could do this with any point. If I picked this one, say, I don't even need to know the x value, the height of the point on the parent function would be the length of this line, but the height of the point on the green graph would only be half. So now we know the green graph matches the curve y equals 0.5 square roots of x.